Yeah. So on the last, not the last Malcontents, but the episode before the last Malcontents, we have Dave Friedman on.
Yeah.
And we got in this conversation where I asked him what his favorite amplifier was.
So, Dave, what's your favorite amp of all time?
Oh, really?
Yeah.
I have a
That's why most of them are in the witness.
I have a 6850 watt Plexi Marshall that I love. That it's a long story, but he made it sound the way it does.
And he brought up his 50 watt Plexi.
Right. Which I had worked on.
Exactly. And in the course of talking about that amplifier, it was kind of almost a comedic effect. He was talking about how it hadn't sounded right until he brought it to you.
And yeah, he bought it for $300 or something, and it had been modified. So he brought it to me, and I just put it back to stock.
But you made this comment on the show where you're like, yeah, I just put it back to stock. But kind of the punchline was that I just biased it correctly.
Yeah. And that was probably one of the things that a lot of people that modified amps didn't understand at the time. Well, first, before you do anything to it, you have to do whatever you can to put the amp in its proper operating condition before it gets modified.
Got it. That makes sense. Let's find out what we really have here.
Because a lot of times somebody would just buy something and they don't know what they bought. They don't know what's going on inside.
Yeah.
They don't know if it had been repaired badly.
Sure.
And a lot of things did get repaired badly or use substandard parts or
just
so right around that time is I met Dave, and he had this amp that he wanted to get right. So I unmodified it and put it all back to stock and set the bias. And then he told the story later on. He took it to somebody else and had it modified, and then by that time he was starting to tweak amps himself, and he undid whatever modification. I think Reinhold did one, and somebody else did one, and he ended up messing around with it, and then he put it back to stock. And that amp at that time had Telefunken power tubes in it. In around 2000, he replaced the tubes with JJs, which were, I think, probably called Teslas at that time. And then he just replaced them again yesterday, because I told him I wanted to borrow it. He said he thinks it needed a tube. I said, all right, well, either replace it or just give it to me as it is, and I'll replace it.
Yeah.
So he decided to get into it and set it up the way he really liked it.
Okay.
And so he put JJs in it, and he biased it to where he says he likes it.
Okay.
And so we'll see where he likes it, because there's two things that he likes. And one of them is the way he has it set right now, which is the way he would set it for a customer coming in off the street. This is the way I think it should be. And then the other way is, this is the way I actually run the amp, which is he uses Variac most of the time when he's goofing around with it. He puts it on a Variac, and then he rebiases it accordingly because he's running at a lower line voltage. So we'll look at that, and then we'll compare that to where I probably set it originally, where he felt like, oh, she made it sound good, which I think is probably, well, we'll see. Because JJs have a characteristic, generally having a slightly higher transconductance than other similar tubes. So typically you would apply more negative bias voltage to them to get them in the same range that a mullet reissue or even an original mullet, for example, would be set. And then we'll play around with his Variac settings and see what we can glean from all of that.
Excellent.
To business.
Okay, so before we hop into the procedural element of this presentation, can you walk us through the relevant gear that we're going to use for biasing?
Well, let's just work from left to right then.
Okay.
I've got a LCR meter, which is a sophisticated test meter for testing inductance, capacitance, and resistance. We're going to use it to check the capacitors today.
Okay.
And then we've got a voltmeter set to AC volts that is connected to our static test load that we'll use to read the voltage at the output when we're doing an output power test.
Okay.
And then we have a scope, of course, and a digital voltmeter that we're going to use for checking the various voltages that we're going to compare and discuss during the course of the examination.
Okay.
We have a soldering station should we need it. We've got an AC line voltage monitor that's telling us what the AC voltage going to all the other test equipment is, so we can sort of monitor and make sure that we're staying locked down tight.
Okay.
And we're going to want to see that at 120 volts. We're generally going to keep it at 120 volts. And this Variac here is the way we compensate. If the voltage drifts up, we'll turn it down. If the voltage comes down, we'll turn it up.
Yes, people, that is a Variac.
But that's not the main one that we're going to be using for the amp. The amp is going to be connected to another device. We'll get to that in a second. We've got our signal generator, our function generator that we're going to be using to send a sine wave and a square wave to the amp under test. And then we have the lab volt machine, which is actually, it's a 50s, 60s era student lab test equipment that's used to do lab measurements in an introductory electronics course back in the day.
It's in such good shape, it looks like somebody did a reissue of an old piece of gear.
Actually, this was a gift from Josh Fiden at Voodoo Labs.
Oh, wow.
He had gone to some night classes at the local college a number of years ago, and while he was there, one of the administrators said, "We have a whole bunch of electronic test stuff that we're going to unload. If there's anything you want, grab it." And he grabbed this, and then it sat in his shop for about 10 or 20 years untouched. And so when he decided to clean up his shop, he called me up and asked me if I wanted it to stick in my shop for
10 to 20 years,
something like that. And I said, "Yeah, sure, send it." So it was, since he was just giving it to me, I said, "I'll find a way to use it." And the way I have it set up is also as a Variac with a meter monitoring the voltage. And there's a lot of other things that I can test with it, and you decide what output you want to use for whatever voltage function you're using, and then you can patch that particular voltage up to whatever relevant meter that you want to monitor. Current, amps, we've got this is an ammeter. This is a DC ammeter, an AC ammeter, an AC voltmeter, and a DC voltmeter. And each of the voltage meters has a range switch so that you can set the input of each meter to the voltages or currents that you want, and those will be monitoring whatever outputs that you patch down here. So right now I've got the variable AC voltage coming out of here, patching into there, and that also connects to, it says 0 to 135 volts, 5 amps.
Yes.
This says 0 to 120 volts, 5 amps, but it's actually connected to this. So whatever is going up on this meter is coming out here, and that's what we're going to connect the amp to monitor its own AC voltage while we're monitoring other voltages inside.
Okay.
That about covers it.
All right, that's all the gear.
Now this obviously does not have the stock power transformer in it, but it's got the stock output and choke, the stock sockets, the original capacitors, and the factory QC tag.
Now, do you remember what the shape of the components were in when he got it? Was that replaced?
No, I don't.
Okay.
And usually on this tag, you'll see 2 digits for the date. And I don't see those.
Only initials.
Yeah, you usually see a handwritten 1969, 1970, whatever. That doesn't appear to be the case here. So,
Dates and components.
could have been worn off one way or another. The way that we know this is not the original power transformer is because it's got these brackets around it. It's got an N bell on the top with the Drake number. And the leads are coming out of the top and going down the original bolt reliefs
Right.
to send the voltage down to the circuitry. So you've got heat shrink here, heat shrink down there. This is insulation here and there to keep things from arcing against the chassis, because these are
It works.
the I believe these are the high voltage connections. However, so now we flip it over, and
Some of those
it's
caps.
very likely that the power tube sockets may or may not have been replaced. It's hard to tell, but they might be the originals, but there's a lot of goop on them, which means somebody put some goop between the high voltage pins of the tubes to prevent arcing. A variable bias control has been added to this, and I don't think that I did that. I think that was probably in there originally.
Okay. Not originally from Marshall, but originally when Dave acquired the amp.
When he got it, yeah, because it had been modified.
Got it.
This would have been based on the conversation I had with Dave, this would have been modified and I put it back to stock. Now, however, I'm seeing a little bit more information. One of the things I'm seeing is that besides the bias pot being changed, these colors are wrong for these pots and the type of wire is wrong. But of course, like I said, this had been modified, probably had a master volume on and stuff.
Okay.
And all of that had been undone and put back.
Okay.
These capacitors aren't original, but they probably are the original value. And then we've got some silver mica capacitors over here, which are the values of the original, although the original did not have silver
The
mica
silvers.
caps. It would have had ceramic 470 picos, and these are 500 pico silver micas. So they're actually just tiny bit higher capacitance value than the stock originals. And this 33K resistor is not stock. That has been changed. The original resistor value would have been 56K. So I want to say that this capacitor should have been a 250 pico, because that's feeding the tone stack. So we have what one of our brethren out there in the amplifier manufacturing industry calls the Turing circuit. It's a part of the tone stack that supposedly Hendrix had done to some of his amps, where the mid-range was beefed up a little bit by changing this resistor and capacitor value to a higher capacitor value and a lower resistance value to change the tone control operation. Actually gives it a little bit more mid-bark. In addition,
But are the mids haunting? That's what
well,
I want to know.
we're about to find out if the mids are haunting and how haunting they are.
Okay.
We have all the original input resistors from the input jacks to the grid, and then we have this fun little network. Now, what's fun about this, if you look at the circuit board, it's the perforated circuit board. So this is early.
Right.
This is 68-ish.
Okay.
And the original amp did not have this terminal strip on it. That was added.
Okay.
And why that was added was so that
That's interesting.
this additional capacitor and resistor
Yeah, what is this little?
could be installed. What this probably was, it doesn't say. You'd have to go by the serial number, but this looks to me more like a super bass than a super lead. And the super bass would have just had this capacitor here and that resistor behind it.
Okay,
Those two guys.
all right.
But
So when you look at that, what does this mean?
this
What
is
does
telling me
do?
that it was converted from a super bass to a super lead by adding these components and this terminal strip.
And what does that do sonically?
But it makes it play like a super lead, makes it brighter.
Got it.
What it does is that instead of both volume 1 and volume 2 voicings being the same, it makes the volume 2, I believe, brighter and less bassy. Maybe it might be volume 1 that's brighter and less bassy. I don't remember.
Okay.
So that when you bring up the volumes, one will give you more low end thump and the other one will give you more bite and claw, right? So when Dave says that I put it back to stock, now that I look at it, it's stock for a particular type of Marshall, but not stock for the original Marshall that it was. This is kind of an amalgam of a couple of things, but for all intents and purposes, behaving like a super lead, not.
Yeah, and we're not talking about something with, massive preamp
Right.
mod at this point, massive
Right.
volume kind of monstrosity.
So let's try to get a look at anything that looks like it might be an original capacitor or resistor or something and see if we can glean a date code off of it.
You get that from the pots?
Yeah, most likely we're going to get it from the pots. I was looking on capacitor to see if I could get it from a cap, but it's going to take some Googling to get that. It's got a radio spares decoupling cap in it. I don't want to turn it too much and break it, but it's a dual cap.
It's cool looking.
It might be original. And the filter caps, one has been replaced over here, this one, and this one it looks more like an original one.
Yeah, because it's
Yeah.
a little bit scuffed.
So the one that's looking original has a date code of 75/28, which is the 28th week of 1975,
Okay.
which
That ain't
that's not
consistent
original.
with.
This one has a date code of. I actually can't read that. I don't know that one off the
Which
top
number?
of my head.
Oh, you can read the
It's
numbers. you
KB
just don't- yeah.
5833TT. I don't know the delineation of that.
Okay.
So it looks like neither of those capacitors are original, which would make sense because this has been soldered on a lot. Now I don't know when Marshall started putting the paint on the soldering connections, but none of these have that. So either they were all resoldered because somebody felt they needed to be resoldered, or it never had it to begin with. It'd be really unusual to not see any original red paint, but okay, so we went online and did a little research, and I've confirmed for myself that this is a 68 Plexi panel. Metal started in 69. There wasn't a Super Bass 50, but the JTM had the same kind of input configuration, which only had that one resistor and capacitor onto parallel triodes over there, so that these voicings were the same. And that's what this had, and it's been changed to the super lead voicing. The coupling caps in the phase inverter are the correct value, even though they're orange drops now and not mustard caps, but those two kinds of caps behave very similarly, so that would be, except for the tone stack, as I mentioned before, this thing is
The touring circuit.
pretty stock.
And then replaced filter caps.
Replace filter caps, different power transformer, but an earlier era where they were still using the paper wound transformer.
Yeah.
So pretty close to the original construction. The original transformer had solder lugs like these riveted onto the assembly back here, and all those leads were connected to there.
Oh.
So that's why you would see all this wiring change, because there was no tag leads anymore.
I see. And then we have the goopy, non-arcing stuff on the tube sockets.
Right.
And that's pretty much it, right?
Right. So let's fire this thing up. Let's have the AC input connector changed to an IEC, which is pretty normal. Everybody does that. And it's set for 120 volt section. And I'm going to switch this to 8 ohms because that's what our test load is set at. Just for testing purposes, for listening purposes, we'll switch it back to 18 and run it into a 412 cab later. Well, now what I want to do before I go any further is, relative to the plate voltage reading unloaded, because we're still in standby, I want to know where the filament voltage is sitting. So we're going to look at that. And we should be at 6.3 volts on the filaments in order to get an accurate bias reading, and we'll get into why later.
Okay.
All right, so we were seeing some fishy voltage going on in here, and it turns out that in the shipping department somebody was printing some documents, and the recent printer that we bought just sucks all kinds of current when it starts printing, and it was causing our voltages to fluctuate over here. In the meantime, okay, we're at 6.3 volts with 116 volts line. It's not fluctuating because we're not printing anything.
All right.
And now that we have 6.3 volts, we're going to take one more look at the raw AC high voltage secondary, and it should be in the 350 range, and we're at 344, 345, right where we want to be. Yes. So now when we hit the standby switch, we should see about 400 to 450 volts on the plate supply, and we're going to read that at the fuse holder because that's what goes to the output transformer primary.
Okay.
All right, ready to go. Let's switch to DC there. And there we got 445 right on the nose. We're good. Okay, so we've established that we've got our 450 volts on the plates, and now we're going to check the negative bias voltage on the grids, which is going to be right here, and we've got minus 36 volts, which is normal. We're going to translate that into current a little later by using my favorite method, which is voltage drop across the primary. But in the meantime, we're leaving it at Dave's setting. Minus 36 is pretty normal, so we're going to go with that. Press this down, all the controls down, and we're going to feed a sine wave directly into the phase inverter. We're going to bypass all the tone
The
control.
input. Okay.
And to do that, we need a couple of basic little settings adjustments to make here. And that looks right. That looks good. So we have a 1 kilohertz sine wave, and we're bringing it up to clipping, which should be right about there. And there it is. That's a really nice symmetrical sine wave that you expect to see in an amp of this era.
What makes it nice? Why you're qualifying it as nice?
Well,
What would not, and then what would not be nice?
we'll see in just a second when
Okay.
the phase inverter starts to to clip, you'll see it fall over sideways. But like I've said in the earlier amps and in the Plexis, they tend to have higher plate voltages, which translates to more headroom in the power amp stage. And we're going to talk about that relative to the bias settings, because when you have the amp properly biased, the output tubes will be producing their normal amount of gain, their normal amount of transconductance, which means that the phase inverter doesn't have to work as hard to drive it to full output. Now, I'm turning up the signal and staying symmetrical well into the point of clipping, and now I could like this a little bit. Right there, you see the bottom half of the wave,
Yep.
It kind of tips upward. That's the phase inverter being out of gas. It can no longer push the tubes to create more, even though it's practically square wave output. It's going non-linear, non-symmetrical. Now, with a lower plate voltage, you'll see that happen faster, and we can demonstrate that by just turning the plate voltage down. I've turned it down to 95 volts roughly. Now I've put the screws to the phase inverter. You can really see how much the phase inverter is crashing on the bottom relative to the top.
Right.
It's because the power tubes don't have as much headroom anymore, and I'm sending more signal to the phase inverter, which can't push the tubes to produce more output. So it's falling off. Now we go back down to our normal signal level and go back up to our 116 volts that we want to be at, and I'm going to double check that. On 16 is what translated to 6.3 volts on the filaments. Yep. Now we put the screws to the phase inverter. We can turn the presence up a little bit, and that'll increase the gain of the phase inverter, because it's sending less negative feedback to the phase inverter to reduce its gain. And you can really see now how much the phase inverter is lopsided on the bottom relative to the top. Now, in later Marshalls, they tend to have lower plate voltage and lower headroom, and as a result, you hear the sound of that non-symmetrical phase inverter distortion much more than in the earlier amps.
And what does that sound like?
That's the sound that we've demonstrated before on some of the other amps when we had the show that we did all the 3 different amps, and we were using the attenuator to push them all the way into phase inverter distortion, and you notice that it got that more pinched E vowel sound. So what this is doing is accentuating that E vowel.
Okay.
What you're getting with the correct plate voltage for this original amp. Go back up to 116 again. And you have this nice symmetrical wave. Before the phase inverter starts clipping, you get that more of a natural bark, more of a natural ah vowel sound, which is always something that I preferred in amps, and which is a real characteristic of high watt amps, for example. So that is this era of amplifier operating the way you would normally expect it to operate. So now I'm going to, we've disconnected the signal from the phase inverter stage, and now we're going to look at the voltage drop across the transformer, output transformer primaries. So here we have, actually I have to do that with DC. One side is 1.3536 volts DC, and the other side we have 1.4. Now normally this output transformer will have a DC resistance of about 25 ohms. So to translate that voltage drop into idle current, we take 25 ohms and divide it by the voltage drop of the primary. So we're at 1.36, so we'll call it 1.36 divided by 25 gives us 54 milliamps. Dave said he biased this to 40. So one of two things, either the primary DC resistance is higher, which this being a 50 watt amp, 25 ohms is usually a 100 watt amp, and this is a 50, so the DC resistance will be higher. Not necessarily double, but it might be. It's kind of difficult to test that under load with voltage on it, but I'm going to give it a shot. See if we just get in the ballpark. So we got 46. Okay, so I was calculating based on 25 and we're at 46 there. And over here we're at 44. It's usually a 2 ohm difference because the secondary and primary are not always exactly the same amount of DC resistance per foot because there's more wire on one part of the secondary than the other. We discussed before, because one half of the primary is wound right at the bottom of the bobbin and the other half is wound at the top, which is going to be longer turns of wire.
Mm-hmm.
And so one side is going to be a little bit different than the other, and that's normal. So now I'm going to go back to the 1.36 divided by 46 instead of 25, and we get 29.5, and Dave said he biased it at 30.
Okay, then.
So now we're all on the same page. Now I tend to like to run the idle current closer to 35. So let's go back to looking at the clipping point and just observe something very simply here. What we're going to observe is that when we get up to the point of clipping, we see a little bit of crossover distortion right here. And we got a chart that we'll show you later that sort of exaggerates what crossover distortion clipping looks like.
Well, we'll pop it in right now. So you're pointing it out here.
I'm pointing it out here
screen.
because I'm going to show you what happens when we increase the idle current from 30 to 35.
Okay.
So there's our 1.36 that we were at, and we're going 300 millivolts more. Let's see what that gives us. 1.6 divided by 46. That's 34.7. Okay, there's our 35 milliamps right there. I just increased it 5 milliamps. Now what do we get? Once we hit clipping C, now we have a nice straight line right there. We've eliminated the crossover distortion.
How did you do that?
We increased the idle current 5 milliamps.
Now, why would Dave prefer running it at 30 with crossover distortion versus this 35 that smooths it out? Obviously, it's just different, horses for courses.
It's just a matter of personal taste. It may be relative to the type of tubes they are. Like I said, they're JJs. Generally, JJs have a little bit more mid-bark to them.
Okay.
And a little bit more transconductance. So you may not hear the crossover distortion as much with JJs as you might with, say, a pair of Mullers.
Well, let's talk about this then. When you first had your hands on this amplifier back in '88 to 1990, it had Telefunkens in there, correct? Contrast the characteristics of those Telefunkens with these modern JJs.
Simply, the modern JJs tend to have more mid-range bark to them.
Okay, all right.
And the Telefunkens and the RFTs that they probably were, which were also the company that made the tubes for Siemens, and later Mullards and the like. These are the current production Mullards.
Okay.
And this is a 1990s Siemens. The branding is off of it because it'd been rebranded with our VHT logo at the time. But you can see that the construction is very, very similar. And
I can't really tell the difference.
they have a similar getter arrangement.
The panels up top are a little bit higher.
Yeah, little minor things. But overall, they're a very good replication of the RFTs. My understanding is that they're made on the same machines that the RFTs were made on. All right, so those would give you a more linear, sort of an open sonic palette than the JJs.
Which is probably your personal preference,
My
correct?
personal preference.
Yeah, yeah.
Given that,
Higher plate
especially
voltage.
given that this tone circuit has that extra sort of mid-range bump in it versus what the stock one had, that would be saying that.
You mean coming from the touring circuit?
That's right.
Yeah.
And that would be saying that Dave really digs his mid-range.
Yeah, which makes sense.
Makes total sense. Now, the fun thing is that Dave says he normally runs this amp at 90 volts, and then he runs the current up higher at 50 milliamps. So, I'm going to drop the line voltage down to 90 and test that theory and observe why he might like that.
Okay.
So we've set the AC voltage to 90, and I'm going to show you something interesting in just a minute. Now I take the signal off of the phase inverter while we're doing this because any signal bleeding, even though I've got the level turned way down, any signal bleeding into the phase inverter from the signal generator will cause the bias reading to be odd.
Oh, okay.
So everything that you do when you're setting the bias on an amplifier has to be predicated on that you don't have any external circumstances weighing on your measurements.
Right. It's kind of like controlling for experiments.
Right. And you really need to
You don't
do
want
that.
your confounding variables mucking things up.
Right. Okay, so here's the deal. At 90 volts, now our filament voltage is 4.9, just under 5 volts. Okay, let's do a little math.
No!
Yes!
You do math. I'll stand here and hold a phone.
120 times 0.7. 120 times 0.7 is 84. 120 times 0.6. No, I want to go the other way. 120 times 0.75 is 90. Okay? So, I don't know what plate voltage Dave was at when he set the bias on this.
Sure.
But it's set to 30 milliamps, and he said he set it to 30. So, by my reckoning, 116 was the voltage that gave you the proper filament voltage on the tube so that they were operate within the parameters that are designed to operate.
Right.
And he set the voltage for 30. Either he thumbnailed it and it was 28 to 32 in that range, or he was reading it at 116. So if I take 116 times 0.7, 116 times 0.75, 116 times 0.75, 87. So the difference between 120 and 116 4 volts, that means that the Variac set at 90 down from 120 is 25%. Set at 116, that 25% becomes 27% because it's 87 volts. Close enough for our purposes. But what we're finding with 90 volts on the input is that we have 5 volts on the filaments. So now we want to get the bias up to, he says, 50 milliamps with 90 volts on the mains. So to get that, we just basically do the opposite. 1.6 divided by 46 is 34. So 0.050 times 46 is 2.3. So that means that we had our voltage drop set at 1.6. To get it up to 50 milliamps, we have to run this voltage drop up to 2.3. Let's try it, shall we?
Mm-hmm.
Give it to me. Oh, I have to turn the voltage on and have my fingers in there.
Ooh.
And touching the chassis while I'm doing all this. So
That'll
you can
give you
see that our voltage drop went from 1.6 down to 1 when we knocked the plate voltage down. So now we need to get this way up there to 2.3. So he says he sets it to 50 milliamps when he sets the plate, the mains voltage to 90. However, when we turn the bias knob all the way up, we don't get 50, we just get under 50.
Interesting.
So, again, he's probably talking in terms of just approximations. We're at 2.3, so let's just take 2.1, which is the reading we got, and divide that by 46 to see what we get. 45. Okay, so give or take 5 milliamps, sure, why not?
Do you want to touch something in there you don't want to for entertainment purposes?
No.
Okay.
If it was my amp, I would, but if I touch something on this and things don't go well, it'll be my ass. Now look at that. At 90 volts, we've got a nice straight line, no crossover distortion when we're clipping. And we're pumping quite a lot of signal into it before the bottom starts going non-symmetrical.
And like actually right about there, the top and the bottom are similar.
Yeah, and of
It's
course when
not-
you overdrive the phase inverter stage, you start to see crossover distortion. But right at the onset of clipping, which is, I'm reading 14 volts there, 14.3, we'll call 14.5 times, we square that and then divide it by 8 ohms, which is our test voltage, and we get 26 watts, which is half. So by setting it at 90 volts, we're getting and running the idle current at 50 milliamps, we're getting exactly half power out of the amplifier. Now, let's look at that 0.050, that 50 milliamp reading. Let's look at that. And I want to kill the signal for a sec and check the plate voltage with all of this going on. And we got 336 volts on the plate now. So 50 milliamps times 300, 0.050 times 336 is 17 watts. Now the maximum dissipation of an EL34 is modern one these days is like 25 to 30.
Okay.
So let's just say 25. 9.7. Right? 0.050 times 336. So that's 70% dissipation at that lower plate voltage because of the Variac and the higher current. That's right where you want the power tubes to be. 70% dissipation to get a nice clean sine wave. All right, so now when we went back to the 450 volts times 0.0, let's see, we said 35 milliamps. We're actually a little less than 16, 17. So again, we're right in there about the 30% dissipation. So all the numbers seem to be lining up that when Dave turns down the Variac and readjusts the bias, he compensates for the plate dissipation by jacking up the bias. And that all makes perfect sense.
Big surprise.
Yeah. The big difference is you'll hear it sound. You'll hear a little bit of an anemic thing, but you overcompensate for that by the tubes that have a little bit more mid-range and the tone control circuit that has a little bit more mid-range, and you get this bark.
While it's spongy.
Yeah. And Dave says that he gets a pretty nice sort of a brown sound vibe out of it by doing
I'm
that,
sure.
of course.
Yeah.
So we'll go we'll go back to the studio and we'll crank this up into a power load and stream it live, and we'll have it opened up so we can set it these two different ways. Perhaps we'll do something like that, and give you a sense of what it really sounds like with these different settings going to happen. And I don't think we need to belabor that too much. This has got the JJ power tubes. The preamp tubes are Shuguangs, which are Chinese. So earlier Chinese tubes that Dave says have been in there a long time. And sure enough, who knows how long they've been in there, but they feel a little dirty, so they've been in there a while. And the last thing that we're going to do now, while we have it open, is check the caps, because Dave mentioned that, I might consider replacing the filter capacitors. And I'm really going to focus on the power supply caps, because those are the ones. Now, remember, we discovered that one of them had been replaced in about 1975.
Right, and then the other one looked newer than that.
Yeah. So this capacitor is wired in parallel. So the two sections of it we're going to be reading simultaneously.
Now, is that typical?
Yeah.
Okay.
Because it's doubling the value of that capacitance. It's a dual cap.
Okay.
So each of its halves will be contributing to the total capacitance value. So we're reading 127 mic. All right.
Got it.
Okay. So let's look at the capacitor. 50 plus 50 mics. So each section is 50. When you parallel them together, it's 100.
Right.
typical filter capacitor tolerance is 20 or 30%, plus or minus 20 or 30%. So at 100, we're reading 126, 127. So that means it's plus 27%, which is perfectly acceptable. That means that capacitor is still quite
Now,
good.
is that perfectly acceptable for the time period that those caps were manufactured? Are the tolerances like tighter these days?
If you want them to be, you will get them that way. You can specify a full range of capacitances with tighter tolerances, wider tolerances, higher temperature ratings, 85 degrees C versus 100 degrees C,
Okay.
which is the maximum operating temperature, and 50 volt surge, 100 volt surge, depending on your application. You've got a lot of variations that you can select for. You probably had a lot of variations before that you could select for, but I think it's a lot more refined, and
Sure.
there's a much broader range.
Well, now
of
we
the
have,
different types.
any way you want it society. So I was just wondering if,
Yeah. So now we're looking at the other capacitor, in which the two sections are separate, and it's a much older part. But
this is interesting.
this one is reading 90 mic on one side and 48 on the other side.
How about that?
So, not exactly sure how much of that is trying to test it in circuit versus that it's going off spec a bit. Now, off spec in a capacitor often means that it goes higher than it's supposed to, rather than lower. Now I'm reading this with a regular capacitor checker, and it's telling me that this 50 mic cap is 210. So this is what I usually find. My multimeter is less accurate testing stuff in circuit than an LCR meter, and that's why
Well, I think we saw that when we were doing the
concert
The
amp,
concert.
Super Reverb, yeah, same thing. So here we are again, 88 and 48.
Same.
Same thing. So let's just look at it to be sure. Again, this capacitor was made in 1975. It's a 500 volt cap, and it's 50 and 50. And then let's just look at this radio spares 32 mic
Yeah.
over here. This is, again, a dual section capacitor, 32 mics on each side. And from one side, we're getting 26. It's right in the ballpark. And the other side, we get 26. Nothing wrong there. So probably I'd say if you were really adamant about replacing a capacitor, I would replace the oldest, this one,
The 75,
Because-
circa 75 cap.
because that was pretty far off. That said, when we were looking at the sine wave on the scope and we had it up to clipping, you didn't see any ripple. If one of those capacitors were not properly smoothing out the DC, you would have seen all kinds of ripple, and ripple would take the form of two lines just looking like they're getting really blurred.
Yeah.
It was perfectly flat on top until we really put the screws to it. So
You probably wouldn't replace it.
me personally, I wouldn't.
just
Unless
know
I
you
was
by now.
really, really bored, or maybe stuck at home with COVID again. And if I was stuck at home with COVID again, I wouldn't have the motivation to do it. So I still wouldn't do it.
Spoken like a man with experience.
Yes. So I think that we had some interesting experiences here with this and playing around with the Variac. And I'm going to set this back to 35. Or I'm going to set
30,
it back to
right?
Dave's spec
Right.
for the full line voltage, and we can go back to studio and bang on it before we mess with it some more. But I think it's really interesting that the importance of not just variacing an amp, but its total operating condition when you do that is going to change.